I can have a bit of fun with graphing. If I already know the graph of y equals f of x, and suppose I just add a constant to it, then that just shifts the graph up by c units. So we've done a little bit of this before with quadratics. For example, if I know the graph of y equals x squared, which is thus just this parabola opening upwards with vertex at the origin, and if I add 1 to the formula for the function, then that just takes the old parabola and shifts it directly upwards by 1 unit. So every point moves upwards by 1 unit. And if I subtract a positive number, of course c is positive there, if I subtract such a c from the formula for the function, then that just shifts the graph downwards by c units. If I apply f to x plus c, so this is a composition of functions. This isn't the same as just adding c to the entire formula. For example, if I take the formula for x squared and apply it to x plus 1, then this shifts the x values on the graph to the left by 1 unit. So this shifts the entire graph over to the left by 1 unit. If I take my original function y equals x squared and I add 1 to the x, so I'm looking at f of x equals x plus 1 squared. That's the composition of the square function with x plus 1. Then it just moves the graph of y equals x squared to the left by 1 unit. So the vertex in particular moves over to the point -1, 0. If instead I subtract 1 from the x, then that moves everything to the right by 1 unit. I can compose these operations. Suppose I want to draw the graph of y equals x minus 1 squared minus 1. Well, I'm going to do this in 2 steps. I'm going to start with the graph of y equals x squared, which I know to be this very nice parabola with vertex at the origin. I can either transform it to x squared minus 1 or x minus 1 squared, but I must make sure that I go step by step. So the next thing I'm going to graph is y equals x minus 1 squared, and the graph of that is the old graph of y equals x squared shifted over to the right by 1 unit. So the vertex of the new graph is at the point 1, 0. And that's the graph of y equals x minus 1 squared. And then lastly, if I subtract 1 from the whole thing, I get that graph shifted downwards by 1 unit. So the graph of this new function is the graph of x squared shifted to the right in the last step by 1 unit, and then this one gets shifted downwards by 1 unit. So the graph looks something like this. And there's a better picture here that should go through the origin. But the important thing here is I go step by step with this process, and I must be very careful of the order in which I shift things. It must correspond to the steps, and the rules I'm allowed to use are listed here. So I would apply one of these rules in each step. Let's look at the graph of f of x equals the absolute value of x minus 1. Well, we know that the graph of the absolute value of x looks like this. And if I subtract 1 from the x, then this gets shifted to the right by 1 unit. So I have this V-shaped graph. The pointy part is at 1, 0. How would I express this as a piecewise defined function? Well, remember, the absolute value of x is x if x is greater than 0, and it's minus x if x is less than 0. So the absolute value of x minus 1 is x minus 1 if x minus 1 is greater than 0, or greater than or equal to 0 if you like, and it's minus x minus 1 if x minus 1 is less than 0. And now I can tidy up that description a bit. That's x minus 1 if x is greater than or equal to 1, and if I distribute the minus, I get 1 minus x on the bottom if x is less than 1. So that's a description of the absolute value of x minus 1 as a piecewise defined function, and its graph looks like this. We saw before when we were dealing with quadratics that if you multiply by a constant, the graph just stretches. Suppose I take a number c bigger than 1, and I know the graph of y equals f of x. If I multiply the formula for f by this c, it might be 2 or 5, then the graph gets stretched vertically by a factor of c. So it gets magnified in a vertical direction. And if I multiply by the fraction 1 over c, then it gets shrunk vertically by a factor of c. Now if I multiply the x by the c and then apply f, then the graph shrinks horizontally by a factor of c. And if I first divide the x by c and then apply f, then the graph gets stretched horizontally by a factor of c. And if I multiply the entire formula by a negative, the graph gets reflected through the x-axis because all of the previous y's on the graph now become their negatives. And if I multiply the x by a negative and then apply f, then the graph gets reflected through the y-axis. Now we have some operations on the sine function shown here, and remember that the original sine wave looks like this between 0 and 2 pi, and then it just gets copied on every subsequent interval of length 2 pi. And suppose now that I multiply x by 2 and then apply the sine function. C is 2, and I'm multiplying x by c and then applying f. The graph should shrink horizontally by a factor of 2. So what does that mean? That means that the wave on the original graph that was spread out between 0 and 2 pi is now completed on the interval from 0 to pi. And then, of course, the rest of the graph is shrunk horizontally in the same way. So we have this kind of accordion effect with the graph being pushed in so that the length of the waves is shorter. On the other hand, if I multiply the whole equation by 2, then the wavelength remains the same, but the amplitude of the wave now becomes larger. So the waves get stretched, the upper parts are stretched from 0 to 2, and the lower halves of the waves get stretched from 0 to -2. So the wavelength remains the same, but the height of the wave changes. The graph gets stretched vertically by a factor of 2. In this example, I'd like to draw the graph of 2 times sine 4x. So I would start by drawing the regular graph of sine, which does one complete wave between 0 and 2 pi. So the blue graph is the graph of y equals sine x. And then I would draw the graph of g of x equals sine 4x. So what happens when I multiply the x by 4 and then apply the sine? The graph shrinks horizontally, so the wavelength shrinks by a factor of 4. So now the graph completes a wave over an interval of length 2 pi over 4, which is an interval of length pi over 2. That wave just continues over every subsequent interval of length pi over 2. So here the wavelength is pi over 2. When I multiply sine 4x by 2, the amplitude of the wave in sine 4x gets magnified to 2. So the new graph has height equal to twice the old wave, or depth, depending on where you are. So finally, this graph oscillates between 2 and minus 2, and it repeats itself over an interval of length pi over 2. So the amplitude of our wave is 2, and the period is pi over 2. Let's see if we can sketch this final example. F of x is 2 minus sine 4x. From our previous example, we have sine of 4x is a wave-like function which has a period of pi over 2, and it looks like that. Now what happens when I multiply that by a minus? Let's call the new function hx equals minus sine 4x. Well, remember, if I multiply the whole thing by a minus, it gets reflected in the x-axis. So this is, if you like, the opposite wave. Okay, it's not the greatest drawing ever, but it's something. And finally, f of x is what I get when I add 2 to this. What happens when I add 2? Well, the whole thing just gets shifted upwards by 2 units. So everything just gets shifted above the x-axis. So this point with y value equal to minus 1 gets shifted to here, and this point with y value equals 0 gets shifted to here, and this point to here. So the wave looks like this. So it's the yellow wave, except it just gets shifted upwards by 1 unit. And again on the other side, and these waves are getting out of control. So that's the graph of y equals f of x. And here we have a couple more examples. If we're looking at x to the power of 1 over 4, we know that the graph looks something like this. It's kind of like the square root function, except it's a little flatter for x bigger than 1 and a little steeper between 0 and 1. When I multiply the whole thing by a minus, then it gets reflected in the x-axis, so the graph of y equals minus x to the 1 over 4 looks like this. On the other hand, if I were to change the x to minus x in the formula, then it would get reflected through the y-axis, and the graph would look like this. Let's use the graph of y equals the square root of x to graph y equals 1 minus 2 times the square root of x minus 3. Well, we'll start with y equals the square root of x, and we'll build this formula up in steps. Y equals the square root of x looks something like that. And let's now graph y equals the square root of x minus 3. Well, remember, when we subtract 3 from the x, this just shifts the whole graph to the right by 3 units. So the start of this graph is now at the point 3 on the x-axis, or the point with coordinates 3, 0. Next, let's multiply by negative 1. And this basically just reflects the previous graph in the x-axis. So it still starts at the point 3, 0, and it looks like that. And y equals negative 2 times the square root of x minus 3 kind of looks the same, except it's been stretched vertically by a factor of 2. And finally, if I just add 1 to this, I get y equals 1 minus 2 times the square root of x minus 3, and that just shifts the previous graph upwards by 1 unit. So now this graph starts at the point 3, 1, and it looks like the previous graph from there on in. Basically, it's the previous graph shifted upwards by 1 unit. these pictures would look a lot better with a little more detail and a little more scale, which of course you can add if you're working through them.